I can say my title. Okay, thanks. Thank you. It's my pleasure to be introduced by Adam and to be invited to speak here. I'm going to talk about work on investigating kind of what can you do with this the training method we all use all the time, just running gradient descent and something. This is joint work with Emmanuel, Pritish, Eran, and Colin. I should say that during the course of writing this paper, 3 of my 4 co-authors had babies. So if you want some kind of fertility omen or something, I'm open to collaboration. I don't know if you're if a pretty good success rate. So okay, yeah. So the basic question we're going to be talking about is like, what do you? We have this learning paradigm. Basically, all of learning we just heard the entire talk. I don't think Ludwig even mentioned how any of these models get trained, because it's kind of obvious. I mean, all our learning is basically done by coming up with some model and then running some kind of version of gradient descent or stochastic gradient descent in it. And these models are usually some kind of deep networks, but you can think of any differentiable model. Okay? And the question we're going to be asking today is, how powerful is this learning paradigm? What kind of learning problems can be learned by coming up with some model and then just running gradient descent in it? Okay? And I want to, so one way to think about it is essentially what we're doing here, right? We're solving an optimization problem. Let's see if this works. Okay, we're solving an optimization problem, right? We're minimizing the loss on some function. So it looks like we're just doing ERM, but I want to emphasize this is definitely not the same as ERM, right? So for one reason, this is not the same as just doing ERM, is that we're using some specific optimization procedure on a problem that's generally non-convex and very crazy, and generally we're not going to find the global minima. And it's not just some technicality, that we might not find the global minima, but yeah, I mean, usually we do. We really can't pretend even that we find our global minima, because this gives us completely wrong answers, right? So in particular, if we could actually do ERM, if we could find the global minima of the loss in the neural network, we could pretty much learn anything, right? So any polynomial computable function can be represented by a polynomial sized neural network. And so if we just trained a poly-sized neural network, we could learn the class of all polynomial functions, pretty much anything we might ever want to learn. And so this is just, this gives us the wrong answer. And in particular, I mean, pretending this, it's also avoids kind of the question, because the real question to me is like, what are these type of things? I mean, we train with neural nets, we actually have lots of success. What is it? Where is the success coming from? How come we can actually, get all these amazing results by training neural nets? And the success is somehow related in a way, there's some magic property of these problems that we're solving that make them trainable by gradient descent to a new neural net. Okay? And we don't know what this magic property is. And again, pretending that this whole magic property rests with what makes it so we actually get to this global minima. And so it's not, we're not going to get any insight for that at all by just pretending we do ERM. But the other reason we can't really pretend, this is very different from ERM. So what we talked about is how it's weaker than actually doing ERM, but in some sense it's also stronger. So we know that in many cases we can actually effectively learn with gradient descent on models that training them with ERM doesn't make any sense. So over-parameterized models, many of the models we use have many, many more parameters than training points. For such a model, just doing ERM is not actually a good learning rule. There are many empirical risk minimizers that do not generalize well. But when we actually train with gradient descent, we frequently do get to solutions that do generalize well. And we understand this, quite well in some problems, in some simple problems. The simplest problem you can think of is an over-parameterized linear regression problem. It's completely nonsensical. Just getting 0 error doesn't get you anything. We're training gradient descent corresponds to finding a minimum norm solution, which might actually behave very well. Okay, and so again, pretending we're just doing ERM completely ignores that, right? So that might also give us a lot of power. So hopefully what I convince you is that really asking what can we learn by gradient descent is very different from asking what can we learn by ERM. And this is the the questions we're going to be looking at today. So, our learning paradigm is we just come up with a differentiable model, maybe represented by a neural network, and our learning rule is then just doing come up with a differential model, maybe initialization, and our learning rule is just running gradient descent or maybe stochastic gradient descent on this learning rule. What type of learning problems can we learn? What's the kind of power of that? Okay, any questions so far? Okay, okay. So now there's some issue also with how do we run exactly when I say gradient descent. So we will distinguish between using gradient descent and stochastic gradient descent. In particular, this is going to be an important point to ask. And one question you can ask also, which is natural, is there a difference actually between running stochastic gradient descent or batch gradient descent, large mini batch gradient descent, small mini batch gradient descent? And this is also definitely something we'll address. Okay, but just as a prelude to maybe think about, and this is also what led us to ask these questions about what's learnable with the gradient descent. Why is it useful to even ask what type of problems are learnable using some model? So one question that we asked and many others asked is this question of what's learnable with gradient descent on a neural net that's not learnable using a kernel. So this is a very natural question to ask, and then this is exactly this type of question where you're asking what's the kind of learning power. You have a general learning paradigm. My learning paradigm is maybe doing gradient descent in a neural network, and somebody else's learning paradigm is choosing a kernel and fitting a model with that kernel. So with regularization in respect to that kernel. Can I learn anything that by picking a model that the other person cannot learn by picking a kernel? Okay, and this is of course motivated. There's been lots of discussion about viewing neural networks, approximating neural networks as kernels, right? So if you think in a certain regime, the neural network kind of never escapes its linear approximation. In that case, basically what you have is just a kernel method, this neural tangent kernel, and then learning just corresponds to solving this L2-regularized problem or kernel problem. Okay, and this is kind of a very, from my perspective, very disappointing view of deep learning, because it would suggest that what we can, the things we can explain using this view is only things we can only do with kernels. We already know how to learn with kernels. What's the point? And we want to go beyond that. Right? So can we go beyond that? And the short answer is yes, there are many problems that are learnable using gradient descent neural network, but not learnable using any kernel. And there's been a lot of work in that. I'm not going to go over this table. This is more of an advertisement. We try to really go and collect all the work showing the separation. You can look at our paper for all the details. But one thing I want to emphasize is that many of these separations are not like as extreme. Like what they show is that you can get, you can learn with both methods, but maybe you need more samples with the kernel method, or maybe the error you can get, there's some difference in the errors you can get. We really ask, can you have like an extreme separation where you can just learn something perfectly well with a neural network by gradient descent on a neural network and not learn pretty much at all using a kernel? And this is and the answer is yes, and you can do that, see that in a fairly easy problem. This problem is biased sparse parities, right? So here we have the output is just a, okay. The output is just a parity over log n, and is the input dimension many bits. And the bits though are biased. So each bit has a bias of, it's more likely to be 1 than 1 or 0. It's more likely to be 1. Okay? So this problem is actually very easy because there's still enough correlation. All the bits that are participating in the parity have enough correlation to the target. I can easily identify them. Okay? But I cannot do this with a kernel method. A kernel method cannot learn parities of this size. No polysize kernel method. No kernel method can do this with polynomial sample size. So the question is, can you do it also by training a neural network? And the answer is yes. And the reason I'm showing you this neural network is because I think it captures kind of what you can do with gradient descent. Okay? So what happens in this neural network? There are two pathways to the output. One is through just a linear function, and this picks up. So the first, what's going to happen is we're going to pick up all the correlations. All the bits are actually correlated to the output through this pathway. Okay, so that's kind of in the first step of gradient descent. But then after we did that, we're going to actually not use this pathway at all, because there's another pathway that goes through a kind of a parity that's hard coded into the network, right? So again, we don't know what the support of the parity is, but that's going to be picked up in the first step. And then we're actually using these things for a completely different thing, right? So this is something that kernels inherently cannot do. Yes.
All the bits are biased, or only the ones?
All the bits are biased. So all the bits are biased. Yeah. So we'll mention maybe then if only the bits in the support are biased, that also can't be learned by a kernel and can super easily be learned by like anything, right? In this case, but we did want to restrict it to problems where the input distribution is fixed. So we're not leaking information to the input distribution. Actually, I'll mention that at the very end if I have time, which I probably will not. Yeah, so here all the bits are biased. The thing is, this bias just creates, because all the bits are biased, the other bits in parity are biased. So I have that maintains some correlation. There's a polynomial correlation between each bit in the actual parity and the output. Okay. The point here is that what we did here is so what we did here is we kind of used gradient descent to do, like in the first step, it's doing something fairly different in the second step. In the first step, it's kind of identifying which bits are linearly correlated, and then in the second step, it's actually saying, oh, I can actually use their parity. It's hard coded and doing that, and that's kind of the type of way we're going to be using gradient descent later on. So the bottom line here is here. This shows an example where you can get at most a polynomial edge, and no kernel can get better than some polynomial diminishing edge, and we can learn perfectly with the gradient descent. But the thing is that in doing this example, we actually had to devise this, show this neural net and build it and then analyze it and analyze gradient descent. It was actually kind of a pain. And in doing this, I realized, I mean, can we just have relate training with gradient descent to models we're already familiar with, so that in order to prove these kind of guarantees, in order to argue about what's possible with gradient descent and what's not possible with gradient descent, we can just refer to results we already know or to just the simple models that are easier to analyze. Okay, and this is what we're going to be trying to do here. Yes.
Isn't that from a paper by Daniel and Malak?
No. So the paper from Daniel and Malak did what was mentioned here. The
bits are completely that are part of
yeah, but the differences in that paper, the input distribution itself, this distribution over X leaks the output. So the input distribution is not it's not a fixed input distribution, it's independent of the function. Here
it's a mixture. Half the time it's exactly the parity,
right?
Bits, and the other half the time it's just a parity on some uniform assignments in bits.
No, in their paper, the input distribution of X was a mixture distribution, where half the time it's just those bits, right? Which means that I can ignore the target and just look at the input distribution.
Well, the target is then just the parity of all those bits.
Yeah, but okay. So in technical perspective, the difference is this is not it. The input distribution, you have if the learning problem is learning parities, you don't know what the parity is, then the input distribution is not fixed. Here, the input distribution is fixed. Right, so the input distribution here doesn't have anything to do with the parity; it's fixed. Okay. So that's what I wanted here. I mean, the details. I should say that we'll maybe go back to the end. I don't want at this point to dwell so much, but on the technical level, that's the difference between Daniel and Malak and here and this work, right? So.
And also, if you wanted a simpler example, you could just use a single ReLU activation. We know the gradient descent. Learn that. It's
So again, so that's I really rather not go into this now. As I said, there are many separations, and I think the single ReLU is in this table somewhere. It's in fact the first thing in this table. Okay, so for single ReLUs, we get a separation, but it's not a separation between not having any edge or just having an arbitrary polynomial small edge and having and being able to perfectly learn it. You can get an edge for a single ReLU also with a kernel. It's just not going to be. You can get a.
It's exponential and epsilon with a kernel.
What?
Exponential and epsilon.
So let's talk about it. Exponential and epsilon. What's epsilon? Right. But you can get for any constant. I can get any constant error with a kernel. Okay. So it's just that, as I said, it's a different type. I'm sorry. So as I said, I mean, this is like there's lots of different separations here, and I'm just showing an example result for one particular separation. I mean, these. Okay. So question there. Okay, sorry, there was a question. Okay, let's oh wow. Okay, we haven't even started the talk, so where are we? Okay, right, okay, so let's start the talk. So the question is, what can we learn with the gradient descent differentiable model? And in particular, can we go beyond kernels? We already know that we can go beyond kernels. Oops. but maybe we can learn anything, maybe anything that's learnable, we can encode as gradient descent, or what I mean by anything that's learnable using some method using M samples. So this is what I'll refer to as pack learning, and I'll completely ignore the fact that these letters actually mean anything, any words. I just mean, when I say pack learning, I just mean learning based on M samples, or maybe anything that's learnable using polynomial time with M samples, or maybe at least anything that's learnable using statistical queries, right? So that's going to be something we're going to be talking about a lot, is learning with statistical queries, meaning I only query kind of the instead of getting samples, I only query the distribution by getting approximate expectations. We'll see the definition in a second. Okay, so in particular, in all these things, what we're going to be trying to do, just to get the setting, we're going to be trying to relating learning methods. And to keep things simple, we're going to be sticking with binary labels and squared loss. So our goal in all this is to find some predictor f that has small squared loss with respect to the distribution, and we're going to measure the error of if we have an input distribution in an algorithm, the error of the distribution is just the expected error over the expected error that this algorithm is going to get for this distribution. The expectation is over the sampling or any random choices the algorithm makes. And there's also a superroom here. Some of our methods are going to be non-deterministic in the sense that they're going to have all kinds of like allowed choices it can make. Like, for example, if I'm saying ERM is not a specific method. There may be many ERMs. They can choose any one of them, right? So this is an arbitrary choice the algorithm make. This superroom is over all these allowed choices the algorithm can make. Okay? And what we're going to really be saying, is that how to simulate algorithms in one class using an algorithm in a different class. So we'll denote it by saying that I can ensure smaller error with the I can ensure smaller error with class C prime than class C if for any method in class C there's a method in class C prime, so that for all distributions the error I can get with this C prime type method is not worse by more than delta than the error I can get with class C. So this is a very, very strong notion of being able to simulate one class of models with another. So in particular, we mentioned SQ learning and pack learning, right? So we all know that we can simulate pack learning with SQ learning, right? So SQ learning, we learn by receiving tau accurate answers to expectation with respect to the source distribution. We can get such tau accurate answers by actually sampling, which a pack learning method can do. It can sample and answer that. So in particular, if I have a number of samples, it's roughly k log k over tau squared. I can simulate any SQ method that makes k queries, each one of them with accuracy tau. Okay, so this is the type of results we want to get. But again, we want to get that not, and we know that very well the relationship between pack and SQ. We want to get them for gradient descent. Okay, so let's define what we mean by gradient descent. Right, so gradient descent, we have some differentiable model F. We have initialization, W naught, can be maybe fixed or maybe a random initialization, but a fixed distribution over initializations. And we just start with initialization and keep updating based on negative gradient steps. And for simplicity, we're taking here a fixed step size, any step size. The step size is not going to play any role here. Okay, and the gradient is just the gradient of the loss with respect to the parameter. Now, of course, what we actually do is we don't calculate the expectation of the actual population. We don't have access to that. So stochastic gradient descent refers to taking each step based on the gradient that calculated in a single sample x and y derived from a distribution. Okay? And now the parameters here is how many iterations I do, which is also a number of samples, and the parameters. And what we're actually going to be looking what we've done in this practice, when one thing we really want to pay attention is what happens when we change the mini batch. So when we change the mini batch, right? So it means that I get more and more accurate gradient estimates. So my gradient estimates are now calculated not based on single points, but each step I base it on B points. So that's another parameter here. And as I mentioned, an important thing I want to ask is, what is the effect of this B? So in particular, in kind of predecessor to this work, two of my co-author, Emmanuel and Colin, I already noted that the batch size plays an important role here. And what they showed is that with pure SGD, with a batch size of 1, they showed how to actually simulate any pack learning algorithm. So we're as powerful as pack. We can kind of really learn everything in some sense. And we're going to revisit this result today. And on the other hand, if I take gradients on the population, so if I have an infinite batch size, then they show that you cannot go beyond SQ, right? So in particular, you're strictly weaker than PAC, right? So there is a gap here. But so one question we can ask is what happens in the middle? What happens if we have, for example, like a polynomial batch size or some other reasonable batch size? Can we actually simulate PAC or can we not? Like when does it become impossible to simulate PAC here? And also what can we do maybe beyond that point? I mean, if we have maybe we can simulate PAC, we can do something else. But it turns out there's another very relevant parameter here, and that's the accuracy of our calculations. So Colin and Emmanuel's results, especially the negative result, rests in the fact that our accuracy, we have polynomial accuracy, or in other words, we have a logarithmic number of bits of precision, right? So all our gradients are only calculated up to some polynomial resolution rho. So what do we mean by that? We don't actually get back the actual gradient, we get back the gradient. What we use is only the gradient up to some rho. Okay. And again, you can think of log rho as a number of bits of precision. In particular, actually, in our results, the way we'll think about it is just that what you get is an estimate of the gradient with log rho bits of precision. Okay. So you can, I prefer thinking of rho as really the numerical precision you're working with. But in that case, limiting yourself to polynomial rho, again, that's only logarithmic number of bits, seems very weak, right? So what happens if you have if you allow yourself slightly better precision than that, right? Do the results change, and how do the results affect this? And this is all for stochastic gradient descent. Another variant we can ask is, here we're using fresh examples at each iteration. What happens if we really go to just a full batch variant? So in the full batch variant, we collect examples and then just do gradient, take every step on the same examples. So formally, this is exactly the same before, except that the random set of examples, the random set of examples are used in each iteration instead of being independent. Each iteration is just fixed. What happens there? How does that affect the results, right? So I mean, does that break things down, or maybe I can learn also in this paradigm. And so this is kind of the questions we'll ask, and we'll start with Minibatch SGD, so with the stochastic variant, and then return to full batch later. And in particular, as I said, I want to relate this to PAC and SQ. So we already know that in this extreme corner, when Minibatch size of 1, I can simulate PAC. And then we already spill the beans and ruin the entire tension here and tell you the answer. So what I'll show you is that actually you can simulate PAC with any batch size as long as you have good enough precision. And the precision you need is, and you only need polynomial precision, so logarithmic number of bits. In particular, you need your precision to be roughly 1 over b. Okay? And this is fairly tight. Once your precision is too low, so once rho square becomes more than 1 over b roughly, or in other words, if you have fixed precision, once your batch size becomes bigger than 1 over rho squared, then you stop being able to simulate PAC. You cannot go beyond SQ, but you can still do SQ, right? So remember that there is a positive result here, because at least you can do SQ. So this kind of gives us almost full characterization of what we can do with gradient descent. There's a small gap here. But roughly speaking, if the precision is good enough relative to the batch size, we can simulate PAC. Otherwise, we can simulate SQ. And that's it. OK, so let's see how we get this. And as if I didn't already attack you with enough acronyms, I'm going to introduce yet another model. And this model is what we call mini-batch statistical query learning. So what's mini-batch statistical query learning? It's the way you would actually implement SQ learning. Like if I actually ask you to implement SQ learning, how do you implement SQ learning? It's not like you're not going to calculate the expectation of the population and then add some adversarial noise, because you can't actually calculate this expectation of population. The way you're going to work is each time you're going to answer a query based on probably a sample from the population. Okay? So in a mini-batch SQ model, the algorithm kind of works in a similar way. It asks statistical queries, but each statistical query is answered based on an empirical average of B examples from the population, again, with some tolerance or precision tau. And I prefer thinking about it in terms of precision, so numerical precision tau. Okay? And an important point here is that now we're going to ask these queries in rounds. So we get to ask P scalar queries or a P-dimensional vector query each time. The significance of these is all these P queries get answered based on the same mini batch. Okay, so this is important. So in a standard SQ model, you can just ask each query separately. I mean, that you don't gain anything by asking a bunch of queries together. Okay? In fact, you only lose. Here, it is important that we're actually going to answer these vector queries all in the same mini-batch. Okay. Sort of. So there's a honest SQ. There's a we initially called this honest SQ, and then we saw that honest SQ, we felt it's a bit of a misnomer. So honest SQ, there's a paper referring to honest SQ. In honest SQ, the queries are 1-bit queries, and there's no accuracy parameter. And that actually makes a significant difference in terms of the result. No, it's not actually the same. Once it makes a big difference because whether you answer them based on the same batch or not, and also when you deal with accuracy. So these differences, it's not. I mean, we can talk about that later, but the honest SQ model is significantly different from what we have here, and see the results are also different. And again, it does make a difference whether you ask 1-bit queries or not.
Okay, there are already separations between honest SQ.
Sorry, what?
There are separations between honest SQ and SQ.
But they're not the same separations as. Yes. Okay. So and again, our goal here is not just to emphasize our goal here. I think it's an interesting byproduct, but our goal here is not so much to separate between honest SQ and SQ. Our goal is to understand gradient descent. Okay. And this model directly corresponds to gradient descent. Okay, in the following sense. So the way our analysis proceeds is in 2 steps. In the first step, what we do is we simulate any mini-batch SQ algorithm using mini-batch SGD. And this simulation is pretty straightforward. Like the mini-batch SGD precision corresponds to the mini-batch to the precision here, and the mini-batch size corresponds to the mini-batch here. And we have like a completely direct correspondence, kind of one-to-one correspondence. And so we can say that the learning power of learning with mini-batch SGD is exactly the same as the learning power of learning with this mini-batch SQ model. And then this allows us now to forget about gradient descent and just ask about how is this mini-batch SQ model related to PAC and SQ. Okay. Okay, so let's briefly see how much time do I have, because I don't know when we started. So why don't you check? Okay, so let's keep going. Okay. So, okay, I hope you brought lunch with you. Okay, so so how are we going to simulate? How are we going to simulate? Sorry, because how do we do the first step? So our goal is to take a mini-batch SQ algorithm. So Adam comes up with some mini-batch SQ algorithm, and basically like an SQ algorithm that answers queries in this form. And now I want to implement that algorithm using gradient descent. So I take Adam's algorithm and I want to come up with a single objective function, sorry, not objective function, a single model, right, parameterized model, that if you run mini-batch SGD on the loss of my model, it'll do pretty much exactly what Adam's mini-batch SGD, mini-batch SQ algorithm would do. Okay, and so the core of what we want to simulate is we just need to see how to simulate statistical queries. And that's kind of easy. Like a gradient is already a statistical query, right? The answer to a gradient, to a mini-batch gradient is already a statistical query. We just have to be able to encode any statistical query that we want. And that's relatively easy. So the maybe main observation here, which is fairly straightforward, like if we have a linear function, if our model is linear with some is a linear function of the parameters w, where the linear function it's some function of x times w, then the gradient is going to correspond to this function of x, right? This is the gradient here with respect to w. The only thing we need to worry about is also this involves x, it doesn't involve y. And so we have to make sure that we get the gradient is 0. So the type of queries we actually answer, and this turns out to be sufficient, are queries where either are 0 whenever the label is 0 or 0 whenever the label is 1. And that we can control by making sure that the output of the model is either 0 and 1. And so we don't get any gradient, right? The loss is already optimal for the label we're outputting. And we only get a gradient when the label is the opposite. In this case, label equals 0. Okay. So the details here, I mean, you can work this. This is thing you can look at this later. This is not very complicated. Sorry, there's a question. Or? Okay. And so the basic idea here is, again, I mean, a gradient is a statistical query, and we can encode any statistical queries in that. But now we have to encode a sequence of statistical queries. And so that gets a bit hairy, but there's nothing fundamentally involved here. I'm not going to go into over all the details. Now, basically, we set the model up so that each time the function knows kind of how many queries we already answered based on how many of the, so there's a parameter corresponding to the answer of each query, and each time the query depends, we're going to have a linear dependence just on the parameters that are going to receive the answer for this query, and the linear function that's going to multiply them. So the function that's going to multiply them locally, it's a fixed in terms of the parameters based on how many parameters are already non-zero. Okay, so the important thing is that the gradient only is very local. So we just need this to hold locally for each kind of type of weight vector based on how many parameters we already set. Okay, so we can construct this. There's a bunch of like really annoying issues to deal with, the parameters drifting and all kinds of stuff like that. But the good news is that now we only have to do this once instead of every time we want to analyze gradient descent in a neural net. Okay, okay. So what we get here is that we can simulate any SQ algorithm using some differentiable model. I didn't yet mention neural nets, right? This is a crazy differentiable model, right? This is defined in terms of this the choices that Adam is going to make in his SQ algorithm. Okay, but making this into a neural net is actually the easy part, right? So what's going on here? I have some function. This function depends. What we define here is just some function that depends on the inputs, the x, and a bunch of parameters. I can think of these parameters as just weights going on from a fixed bias, for fixed bias term to the function. Okay, and now the key is that if Adam's algorithm is actually a polytime algorithm, then that means I can implement all these decisions of which query to make and all the queries themselves using a polytime algorithm, which means using a polytime circuit, which means I can implement them using a neural net. Okay, using a polytime neural net. So that means that this entire function here I can actually implement using some reasonably sized neural net. Okay? And that gives me the fact that I can now, this means that what I described here is actually a neural net, or can be implemented as a neural net. That means that if the algorithm, so again, there are two parts here. One is that any SQ algorithm, no matter if it's polytime computable or not, can be simulated by gradient descent on some differentiable model. But if this algorithm, this SQ algorithm is polytime computable, then furthermore, this differentiable model can be implemented as a neural net. Okay, yeah. No, it's okay. You can. Very crazy, ridiculous, completely.
And also, you really need stochastic gradient descent.
Okay. Wait. So that we didn't talk about yet. So what we talked about so far is just how to implement mini-batch SQ algorithms using mini-batch SGD. So we didn't touch at all the issue of stochasticity. Right, so that's we're intentionally separating between those two things, right? So in order for this simulation, I don't need stochasticity. In this simulation, I'm going to need exactly the same stochasticity as your SQ algorithm is going to need. Your SQ algorithm, your mini-batch SQ algorithm, is going to use B samples at each iteration, which is exactly the stochasticity that I'm going to use. I'm going to use B samples for each step of stochastic gradient descent.
B has to be very small.
No, this is true for any B. For any mini-batch SQ, you're going to run mini-batch SQ with some B, with some batch size, right?
Full batch.
If you're going to use full batch, I'm going to use full batch.
Yes.
I don't need any stochasticity to simulate it.
Right.
Okay. So we didn't yet touch stochasticity at all. Like this simulation has nothing to do with the stochasticity, right? Whatever sample.
I need to be able to basically kind of look at example by example.
No. The computable function. Okay, let me clarify. The computable function you're simulating here is a deterministic function. It has no. I mean, it could have randomization. That's actually just makes it a bit more complicated because I need to add some random bits. But for now, let's say your SQ algorithm is a deterministic algorithm, right? So each query is a deterministic function of the answers to the preceding queries. This deterministic function, right?
I see. You're embedding this within, because you're embedding this within SQ. Okay.
Because I'm embedding with it. I'm taking your mini-batch SQ algorithm.
I'm just saying that there are problems that we know that you cannot implement with full batch SQ.
Oh, of course, but that's not what. But that's not again. I'm not showing you here. So far, I didn't tell you that you can do anything with SGD. What I'm telling you is anything you can do with mini-batch SQ.
That's what I meant. You're embedding it with
yes, exactly, right? Okay. So now the second question, in fact, So, right, so what I'm saying is just minibatch SQ is exactly the same as minibatch SGD. They're basically exactly the same classes, right? And so now what Adam is, I think, asking is like, okay, fine. So how does this relate to actually SQ learning and in pack learning, right? So, right, the thing is that now when we go to answer this, we can now completely forget about gradient descent. We can now just ask, how powerful are these minibatch SQ queries, right? And as a function of the sample size and of the batch size, okay? Okay, and the answer is as follows. So first of all, the one thing we can already say is it's pretty easy to simulate SQ using minibatch SQ, right? So you can answer for any SQ algorithm. If you want to have an SQ, SLIL has an SQ algorithm that actually expects answers that are within some tolerance of a population, I can simulate any answer to SLIL and with a sequence by averaging a bunch of minibatch SQ queries until I get the as long as the numerical tolerance is not any worse than the tolerance to once, I can actually answer any statistical query on the population by averaging a bunch of minibatch statistical queries. So I can simulate SQ with minibatch SQ, and so this is inside here. So this already tells us that minibatch SGD with any minibatch size, right? So no full batch or huge batch, population with a small batch, can at the very least simulate SQ. So that's already like a useful result. I mean, that means that, for example, for the separation result I showed you before, I didn't really have to show you the network. It was enough for me to say I can learn sparse bias parities with SQ. Done. I never have to show you a network. I never have to like analyze gradient descent. And same for all these other separation results between kernels and differentiable learning. Okay, they're all actually SQ learnable. Okay, but can we go beyond SQ? Okay, so how far can we hope to go? So definitely everything here is included inside pack, right? I can simulate all of these things using, but with samples. So everything lives inside pack learning. Can we actually get to pack learning? And this is maybe to me was the most surprising thing here, is showing that minibatch SQ can actually simulate pack learning as long as we have this relationship between the batch size and the tolerance. So as long as the batch size is not too large relative to the tolerance, or the tolerance is not too coarse relative to the batch size. Okay, so we need the batch size to be 1 over the tolerance 1 over batch size, whatever you want to prefer to think about it. And in that case, then this goes all the way out to pack learning, and we can simulate pack. And again, this result is a result about minibatch SQ, but it translates directly to a statement about gradient descent, about minibatch gradient descent. Does that, Adam, is that kind of what was bothering you before? And this is where the stochasticity comes in. Okay, okay, so I still have to show you how to do this, but it's a statement of the result. All right. Yeah, you're okay. If you're surprised that this is possible, I was also surprised. So I don't know. I was actually always, when I give these talks, now it's obvious to me. So I'm expecting all the audience to sit there and say, "Oh, this is obvious." Maybe this is obvious to you. It wasn't obvious to me. Okay, and the question is,
yeah. I would say from prior work by Abe and Sandin, I would say, it's known that if you allow me individual example access.
Right. If minibatch equals to 1. But now I'm saying I can do it with any minibatch.
But I'm saying that had nothing to do with stochasticity. That, for example, all of these lower bounds will still hold for SQ plus noise. It was more that there you actually, the reason why you can start to implement all of these classes is that I get to actually look at example.
So I would actually, so I think from my perspective, the main message here is that's not the case. That's actually not because of that. I can actually implement anything. The computation, the issue of computation and what computations they do is completely separate from the issue of the mini-batch size in SQ. Okay, maybe we can talk.
I'm just saying it doesn't have to do with the fact that SGD, like I would say conventional wisdom is that SGD is advantageous over GD because there's some noise, it's allowing you to escape local minima. But that's not what's going on here. It's not that there's some kind of noise that's allowing you to compute these functions.
Okay. You don't need the noise to compute the functions. The issue is not computing the functions. I don't know if that's okay. Let's talk about that at the end because this is, I think, an important issue. But they want to get okay. And the question is now, how far can we push it? Do we in fact need this tolerance? Maybe we can do it with less tolerance even. Okay? And the complementary result is this is almost tight when the mini batch size times the squared tolerance at least is larger, and we do need here to be larger than log dimension. Then we cannot go beyond this Q. Right, so there's so we kind of characterize exactly when this mini batch SGD, when is it is small as SQ and when is it large as pack learning. And there's some regime in between, a relatively narrow regime that we don't know. And it's definitely, I actually don't know the answer there. Okay, okay, assuming I do have a few minutes. Okay, maybe I'll do this very quickly. So maybe there are two kind of, I think, confusion here. One is the simulation. And again, I think that the important thing this is maybe part of the discussion with Adam, the simulation has absolutely nothing to do with stochasticity, sampling, anything. It's just like taking these statistical queries and directly implementing them with gradient descent. And the other is being able to leverage these mini-batch SQ queries to actually simulate any pack algorithm. And the key here is what we essentially have to do is we're able to extract samples, right? Once I can extract single samples, then of course I can simulate pack. I can just extract a sample and then feed that into my pack algorithm. So how do I extract samples? And this is, I think, to me, the kind of interesting technical part here, right? So I want a procedure that performs a sequence of mini-batch SQ queries and outputs a sample sampled exactly from the source distribution. So I only have access to the source distribution of the mini-batch SQ queries. I can do this. I'm actually, okay, actually, something. I'm not going to actually tell you how to do this. Let me just tell you that it is possible to do. So this is the algorithm. I'm not going to go over it. We can maybe at the end, if we have time, we can go over it. But the point is there is a relatively simple algorithm that with order n is a number of input bits, or in every roughly order n iterations, it spits out a sample. And when it spits out a sample, it's exactly sampled from the source distribution. Okay. So this is the key here. Okay, let me go. Let's go back though to exactly what we showed and what's the actually how much. I mean, seriously, how much time I have, because I could actually go over that, but I don't know. I feel like my watch. Feel like I'm way over time. 5 minutes. Okay, so then let's me go on and then that's fine. Okay. Okay, so let's let's summarize what we have. So again, what we can say is that as long as the tolerance, I'm just repeating the same thing already for the third time, but just to make sure we're all on the same page, right? The tolerance is small relative to the batch size. I can simulate pack. This result again is completely general, has nothing to do with computation, right? So this is I can simulate with some differentiable model. I can simulate any method based on m samples. When I'm saying method, just like a function from a mapping from those samples to the output. But if the method is polytime computable, then I can also do this with a neural net. Okay, and if the tolerance is high, I cannot go beyond the skew. But anyway, I can at least do a skew. Okay. Okay, so again, this is just correcting a bit maybe the picture we might have had before based on the Manuel and Collins result, that the simulation does not actually strongly rest on the mini-batch size being 1, right? So I can simulate SQ, which is quite a bit with any mini-batch size. And also with any mini-batch size, I can also simulate pack, but I do need to be a bit careful with the tolerance. I mean, I do need my tolerance and the number of bits to be logarithmic in the mini-batch size. Okay. If, however, I have finite precision, then again, I get this separation that once my mini-batch size is too high, I stop being able to simulate pack and I can just simulate SQ. Okay. What about full batch gradient descent? Again, so one of the ways to think about this is, oh, there's an advantage of mini-batch SGD over full batch gradient descent. So full batch gradient descent is a bit different than using batch size of infinity, right? And we still have a limited batch size, but we keep using the same examples. So again, here you can take the exact same two-step approach. In the first step, using the exact same simulation, we can simulate a model, like a full batch SQ model. So now this is the same as SQ, but I answer all the queries using the same sample of examples, right? In the simulation, results are exactly the same. So again, we don't have to worry about all the gradient descent, nasty gradient descent details. We're just back to asking, what can we actually do with this full batch SQ? And in some sense, the sample extraction is even easier here, right? Because I keep having access to the same batch. I can ask as many queries as I want on the same, adaptively on the same number of examples. So in some sense, it's much more powerful actually than before. And in particular, we can at least do what we did before, which is extract, we can extract samples if the batch size is the tolerance is small relative to the batch size. So again, if the tolerance is less than 1/m, then we can extract samples and gradually extract all the samples in the sample and simulate back. And basically, just recover. What we're doing in this case, we're actually doing something even stronger. We can even draw without replacement and even completely recover the sample that we have and just run pack. I should say that here there is a oh, wait, what's going on with the, it's not showing. Okay, so the lower bound, we also have a lower bound here, but the lower bound here is much more disappointing. So before we had a lower bound that says that if where is it? If the batch size times the tolerance squared is high, then we cannot go beyond SQ. And we have kind of a similar lower bound here, but the difference is now the batch size times the tolerance squared has to be higher than something that's polynomial in the number of iterations and number of parameters. And this is a very, super weak lower, and then we can go beyond SQ. But this is a very weak lower bound because it, for any mini batch size and tolerance, maybe I can make up for it by just running longer, having more iterations. Okay? And this lower bound does not preclude it. And I actually think the question here, I think it's important, interesting question, not so much for gradient descent, more maybe for privacy or other applications. Actually, I've looked a bit at privacy. I'm a bit surprised this is not something at least directly covered. Maybe you can correct me, maybe it is. Can I actually, if I have access to the same batch of examples, can I extract samples even with any polynomial batch size, even with constant tolerance? Right. So does that somebody know the answer actually? If I give you these SQ type access to a sample, like you can calculate averages in the sample with fixed tolerance, can you extract this a single sample? Or okay, I don't know. Anyway, the conclusions about so what can you tell us about about gradient descent versus about full batch gradient descent? And we can see that we can actually simulate back with full batch gradient descent with enough tolerance. Again, not so much crazy tolerance, only a logarithmic number of bits of precision. But if we do fix the precision, then at some point we do get we do need to use, do we have a benefit from Minibatch? And again, the main caveat for all of these results, as Adam already mentioned, these networks are ridiculously crazy networks with super specific initialization, right? I'm coding here. I mean, Adam, if Slid starts with a pack algorithm, and then Adam implements it with a Minibatch SQ algorithm, and then I implement it with a gradient descent. On a neural net, my initialization from a neural net encodes the circuit that implements Adam's SQ algorithm that implements Steele's pack algorithm. Okay, that's a completely crazy initialization and not something we would ever use. So nevertheless, and I think it's important to keep that caveat in mind when we think about, what does all this teach us? Like, what did we do all this? Okay, so. And because of this caveat, I'm not entirely sure what this teaches us, to be honest, right? So the questions we're trying to answer here, there's some interesting question here, right. So what this shows is, in some sense, first of all, SGD can kind of go beyond SQ. So when I think usually about training with gradients and stochastic gradient descent, I usually think about just what I'm doing is essentially some form of SQ. And what we see here, this is not true. Right? Like, it can definitely go beyond SQ, even with large batch sizes, right, with some precision. But again, is this really true? I mean, can we really, is the power of neural nets by the fact that it allows us to go beyond SQ? I mean, this doesn't seem to be the case. And I think it's an interesting question. In realistic networks, can you actually go beyond SQ? Right, so you can definitely I can't even expect to simulate all of SQ, but do I effectively, is this effect of using small batch sizes to go beyond, or finite batch sizes to go beyond SQ, something we actually leverage in practice? And I have no idea I actually even answer this. I'm not sure. This work only shows kind of like possibility of that. I wouldn't even say plausibility. The other questions about what maybe Adam was alluding to before, the power of stochasticity in using small batch sizes. Do we actually gain by using small batch sizes, right? So there's a lot of discussion we do. And what we what we see here is that yes and no. So on one hand, we don't really need to use pure SGD. We can actually simulate PAC, as I said, even without stochasticity in the algorithm, even with full batch gradient descent. On the other hand, we do see some benefit of stochasticity if we use finite precision. And in practice, we do use finite precision. And now we have to ask, is the precision we use really logarithmic in the batch size or not? I don't exactly know how to answer these questions for realistic networks. And also, we didn't preclude the fact that you might even be able to simulate PAC even with with full batch gradient descent. Actually, in some sense, you maybe even have more power, right? You maybe can even simulate PAC using constant tolerance, right? So in some sense, maybe you just lose by insisting on stochasticity here. But again, the main caveat here is that all this is with these crazy networks. And I think that this tells us, frankly, fairly little on the role of stochasticity in practice. And there's been several other papers also recently that from very, very different directions looked at this question, which I think is a super important question about really, does stochasticity help us? I mean, do we actually gain by the fact that we're doing stochastic gradient descent as opposed to like full batch or more deterministic gradient descent? Do we gain by having small batches in terms of, so we definitely gain by reducing runtime. That's very clear, right? That we understand very well. But if we don't care about runtime, do I gain in terms of generalization ability? And I think that the jury is still out of this. There's several papers that show that in principle you could gain. The paper by Chengin and Bartlett and Jordan that showed that the implicit bias can be affected by stochasticity in interesting ways. And I think another super interesting paper by Sakari, Kali, and Sridharan, a recent paper that showed that for a certain type of stochastic convex optimization problems, they're actually learnable using stochastic gradient descent, but not learnable using ERM in a very kind of strong way. Again, this shows that there exist instances that for which SGD really helps, but it's completely, these are super artificial problems. Again, it's not clear whether this is actually happening in problems we actually use. And again, I think that an interesting question that Emmanuel and some people maybe even in this room, or at least in this program, are looking at is, can we sort of restrict the class of models we're talking about and say what's so what we kind of see here is that asking what's learnable, okay, maybe that's the one conclusion here, but asking what's learnable with gradient descent on some neural network is maybe not a very interesting question. So we started by saying understanding deep learning by asking what's learnable by ERM is not interesting. That's the wrong answer. So now we're saying, okay, what's learnable by gradient descent on a neural network? And maybe the conclusion here is this is also not interesting because we get this very generic results that really we can do all of SQ and maybe even all of PAC. That's again not a very interesting question. Okay? Because clearly it's not like we can, any specific neural network cannot learn all of anything that's PAC learnable. And so we need to make even more restrictions. So we ask, what can we learn by gradient descent on like homogeneous networks, when it's relatively uniform, when initialization is not crazy. And I don't know how to define initialization is not crazy. I think this is kind of maybe the most interesting thing here. Okay, the last thing I wanted to mention is circling back to kernels. Maybe I'll take another, do I have another minute? No, okay, never mind. Oops. That's fine. So let's just end here. And if you want to read more, both of those papers are in archive. Thank you.
Questions?
Could you just say a little bit more about how this relates to the honest SQ setting?
So honest SQ.
Also, and like in the setting where it's 1 bit, as well as in the setting where it's like maybe real value.
Okay, so honest SQ, the honest SQ model did not have an accuracy parameter, but you're only allowed 1 bit query per round, and in that case, you actually cannot go beyond SQ. So what's really important here is that we are allowing a polynomial number of queries per round. Okay? And in particular, it's not a very high polynomial. All we need is n queries or n+1 queries per round. And in some sense, I can't exactly prove this, but I can argue that if you want to do extraction, you cannot do extraction with less than much less than n queries per round. Okay? So now it doesn't mean that you can simulate pack, right? But in order to do the kind of the type of extraction we're doing of actually returning a sample from the distribution, okay, you have to kind of have many queries. Now, you can the queries we're doing is also single bit queries, okay, but we are limiting as you saw, once you're allowing multiple bit and multiple queries, the accuracy does become important, okay, because if we didn't bound the accuracy, like the honest skew model doesn't bound the accuracy, we can again do anything. And so the things we're bounding are a bit different. Again, the main result for the honest skew is if you ask a single bit query at each round, you cannot go beyond the skew.
The poster session is at 1:30. 1:30. So we'll see you then.
Hey, Adam. Yeah.